Voltage shunt feedback amplifier. This is the block diagram. In this block diagram, two main blocks are there. So the first two block is operational amplifier and the second block is feedback network. Here the input to the feedback network is taken from output of the operational amplifier, which is in parallel. The output of the feedback network is applied to the input of the operational amplifier, which is in parallel with the source input VIN. So this is voltage shunt feedback amplifier. Now this is the circuit diagram of voltage shunt feedback amplifier. So this is the operational amplifier. Here the non-inverting input terminal is grounded. The source input VIN is applied at inverting input terminal through a resistor R1. The output of the operational amplifier is VO. The output of the operational amplifier is applied to operational amplifier inverting input terminal through a resistor RF. That is the feedback resistor RF. The input voltage drives the inverting terminal and the amplified as well as the inverted output signal is also applied to the inverting input via the feedback resistor RF. This arrangement forms a negative feedback because any increase in the output signal results in a feedback signal into the inverting input signal, causing a decrease in the output signal. The non-inverting terminal is grounded. Resistor R1 is connected in series with the source. The closed loop voltage gain can be obtained by writing the Kirchhoff's current equation at the input node V2. So as shown in the circuit, I1 equal to IF plus IB, that is input current I1 equal to the feedback current plus IB. Here the current IB is the overall current uh, will enter into the operational amplifier. See, generally the resistance R1 is very large, so the input current IB is negligibly small. So therefore I1 equal to I1 is nothing but VIN minus V2 divided by R1 and IF equal to V2 minus VO divided by RF. And V1 minus V2 equal to VO divided by A. Therefore V2 equal to minus VO divided by A because V1 equal to 0. So now after simplification we can get the gain of the operational amplifier with feedback minus RF by R, that is AF equal to minus RF by R, and which is equal to minus 1 by B, where B equal to R1 divided by RF. The negative sign in equation indicates that the input and output signals are out of phase by 180 degrees. Therefore, the voltage and feedback amplifier is called closed loop inverting amplifier. The characteristics of voltage and feedback amplifier. First one, inverting input at virtual ground. So in the actual circuit, the non-inverting terminal is grounded and the input signal is applied to the inverting terminal via resistor R1. The difference input voltage Vd is ideally 0. So this is the voltage at the inverting terminal and is approximately equal to that of the non-inverting terminal. In other words, the inverting terminal voltage V1 is approximately at ground potential. Therefore, it is said to be at virtual ground. So within the circuit, the input current IIN equal to IIN equal to VIN minus V2 divided by R1 and IF equal to V2 minus VO divided by RF. V1 equal to V2, that is 0 volts ideally. So VIN divided by R1 equal to minus VO divided by RF. VO equal to minus RF divided by R1. Characteristics of voltage shunt feedback amplifier. Input resistance with feedback. Now we are going to analyze the input resistance of the operational amplifier with and without feedback. The input resistance of voltage shunt feedback amplifier. To find the input resistance, Miller equivalent of the feedback resistor RF, we need to define. That is, RF is split into two Miller components. The input resistance with feedback is RIF, which is defined as RIF equal to R1 plus RIF divided by 1 plus A. Here R1 and A are very large, therefore RF divided by 1 plus A in parallel with Ri is almost all equal to 0 ohms. Therefore RIF equal to Ri. The input resistance of the operational amplifier with the feedback is equal to input resistance of the operational amplifier without feedback in voltage shunt feedback amplifier. Next one, output resistance with feedback. The output resistance with feedback, that is ROF, is the resistance measured at the output terminal of the feedback amplifier. The output resistance can be obtained using Thevenin's equivalent circuit, which is shown in the figure. So here the input signal is shorted, that is input signal VIN is reduced to 0 volts and a predefined voltage source, this Vout, is attached at output terminals as shown in the circuit. So here VIN is shorted and Vout, predefined voltage source having the volts Vout, is applied at output terminal. Now the output current IO is split into two parts. Some of the current IA will enter into the operational amplifier and remaining current IB will enter into the feedback network. IO equal to IA plus IB. Since RY is very small as compared to RF plus R1 parallel R2, therefore IO equal to IA. So VO equal to RO into IO plus A into VD. Here VD equal to VI minus V2, which is equal to 0 minus V into VO. Therefore IO equal to VO minus A into VD whole divided by RO. So finally the output resistance RYF equal to VO divided by IO, which is equal to RO divided by 1 plus AB. Here the feedback ratio B equal to R1 divided by RF. So what is our observation? the output resistance of the operational amplifier with voltage shunt feedback is reduced by a factor 1 plus AB. And similarly, as per voltage series feedback amplifier, within the voltage shunt feedback amplifier, the bandwidth increases by a factor 1 plus AB and the total output offset voltage reduces by a factor 1 plus AB. Thank you.